So we want to begin this unit by talking about the definition of a circle, to be sure that we are all on the same page. You all know what a circle looks like, but by definition, a circle is a set of all points equidistant in a plane that are the same distance from a given point called a center. The set of all points in a plane that are a given distance from a fixed point called a center. It's a geometric definition of a circle. Later in either pre-cal or algebra 2 maybe, you'll come up with a different, slightly different definition of a circle, but it has to do with it being all the points are a given distance from that center point. And in the circle that I have here, we would call this circle P. And if you want to have a shortcut, instead of writing out circle, you can do a circle with a little dot in the center. This would be circle P. That's how you can name that circle. Instead of having to write out the word circle, you may name it this. And circles are named by their centers. When we are talking about a circle, we name it by their center. Now, there are parts of a circle. I'm sure you all know what these parts are, but we're going to talk about them anyway. The first one is a radius. If you've got more than one circle, then we have radii. So a radius is a segment whose endpoints are the center of the circle and a point on the circle. It's a segment whose endpoints are the center of the circle and a point on the circle. So if we look at the circle that I have drawn, what is a radius of that circle? CD. Would it matter if I said DC or CD?
No.
Okay, now when we're going to name it, remember we need to name it. It's a segment, so it's segment CD. Do you see any other radii of that circle?
CS.
CF is the radius of the circle. Anything else? And CE is a radius of the circle. Notice if it's a radius, it's always going to contain that center point as one of its endpoints. If we talk about the length of the radius, then we do not use the segment notation, going back to what we learned at the very beginning of the year. If we're talking about measurement, if we just had CD, we'd be talking about the length of the radius, not the radius itself. All right, a chord is a segment whose endpoints are on the circle. What is a chord in circle C? What's one chord, Hannah? Chord AB. Do you see any other chords on that in that circle? EF. And again, if we talk about the length of them, then we do not use the segment notation. But these are the chords of the circle, and we will be dealing with chords a good bit during this unit. And then finally, the diameter of the circle is a chord which contains the center of the circle. a chord which contains the center of the circle. In this case, which one is a diameter? It's EF. That is a diameter of the circle. If we were talking about the length of the diameter, we would not use that segment designation. So, talked about the radius, talked about the chords and the diameter. We think about the definition of a circle. What do we know about the radii of a circle? Darby? What could you, from the definition of a circle, what could you conclude about the radii of a circle? Leah?
The radius is from the center point to the other side.
Okay, that's a definition of a radius, but what could you conclude about all the radii of a circle? What's the definition of a circle?
So one point zero. Given distance from a fixed point called the center.
Okay, what would we call that given distance? What do you think we'd call the given distance if it's from a fixed point in the center?
I don't know.
What would it be, Darby? The radius. So what can you conclude about the radii of a circle? Cameron?
Could it be that they're all equidistant from?
They're all equidistant, but what else might we say? They're all, Estelle? Congruent. Because by definition of a circle, you're talking about that radius that is a fixed distance from that given point called the center. Well, if all radii are congruent, what could we conclude about the diameters of a circle? All diameters of a circle are congruent as well. And we can determine that simply from the definition of a circle. All right, make it a little swigglier. Okay, so yes, sir. I think we can conclude from what we just said that the diameter is equal to twice the radius. And so I think you've probably worked with the formula before that says that D equals to 2R. So if you're given a radius, you can find the diameter, but if you're given the diameter, you could also find the radius by dividing by 2. Okay, now when we look at a circle, it separates the plane into 3 parts. You've got the interior, pretty much common sense. I is in the interior of circle P. You have the exterior. Exterior to circle P. E is exterior to circle P. And then we have the circle itself. So the circle separates a plane into 3 parts. You can have the circle itself. We have T that's on the circle itself. We can have points that are exterior to the circle, and then points interior to the circle. So those are the 3 parts of the plane that a circle can separate into. We want to look at ways that a line can intersect a circle. We've got 2 different ways that a line can intersect a circle. The first one I have drawn for you, it intersects the circle in one point. Line L intersects circle P in one point. These are coplanar. Okay, so we're talking about coplanar lines, but a tangent line is a coplanar line. That intersects a circle in exactly one point. Okay, in our given circle, the line L is tangent to the circle P at point X, and we call that point X here would be our point of tangency. Now, this is not the same tangent that you did on your homework. That has to do with right angles. This is talking about a line that is tangent to the circle. That means it's only going to touch it in one point. Just one point. Now, the other type of intersection of a coplanar line with a circle is a secant. And a secant is a coplanar line that intersects a circle in exactly 2 points. Is there any way that a line could intersect a circle in more than 2 points?
Yeah.
How?
If it goes through the center.
Is that intersecting the circle, though, more than 2 points? We talk about where it intersects, we're talking about on the circle itself.
Oh, well, not the inside.
Not worried about the inside.
So they're just-
So it's either 1 point or 2 points. Now, this secant there's a trig function also that's a secant. You didn't see that one. But again, it's different than the secant line that we're talking about here. The line AB is a secant to circle C, intersects it twice, but a secant will also contain a chord of the circle. What chord does this line AB contain? Chord, or segment AB. Okay, so line AB is a secant, but it contains chord AB. So a secant will contain a chord. Okay, now when we talk about tangents, we can have common tangents. And a common tangent is a line that is tangent to 2 circles in the same plane. A line that's tangent to 2 circles in the same plane. And we have 2 types of common tangents. You have a common external tangent, which I have drawn here. It's a common tangent and what do I mean when I say it's a tangent line? It intersects in only 1 point. A common tangent that does not intersect the segment whose endpoints are the centers of the circle. I'm going to abbreviate endpoints. A common tangent that does not intersect the segment whose endpoints are the centers of the circle. Okay, and when I talk about the segment whose endpoints of the circle, I'm talking about this segment. Notice that the common tangents do not cross that segment. So we can have common external, and it's easy to see, looks like they're kind of outside the two circles. The other type of common tangent is a common internal tangent. And this is two tangent lines that do intersect the segment whose endpoints are the centers of the circle. So this is a common tangent. That intersects the segment whose endpoints are the centers of the circle. Notice it does cross this segment. Now technically, circles like this have both common external and common internal, even if you don't show both. But they can have both common external and common internal tangents. So common external do not cross the line or the segment that joins the circle's centers. Common internal do cross the line that joins the circle's centers. Okay? We can have our concentric circles. Concentric circles are two or more circles with the same center. Okay, can you think about congruent circles? Congruent circles have congruent radii. That's how you know you have congruent circles. If their radii are congruent, then the circles are congruent. Different length radiuses means that you do not have congruent circles. Okay, here's some examples when two coplanar circles are tangent to one line at one point, then they're tangent to each other. We can have them externally tangent or internally tangent. If they're externally tangent, the centers of the tangent line or the centers of the tangent circles lie on opposite sides of the tangent line. The centers of the tangent circles lie on opposite sides of the tangent line. And you can see in this case, segment MN, that tangent line goes right through segment MN. It's only tangent to both circles at one point. Okay, so if two coplanar circles are tangent to one line at one point, the circles are tangent to each other.
Right.
So circle M is tangent to circle N.
So it's the center of the tangent.
Here you have an example of internally tangent circles. The centers of the tangent lines lie on the same side of the common tangent. The centers of the tangent circles lie on the same side of the common tangent line. So both of these circles are tangent to each other at this point, and they're also tangent to the line at that point. Okay, here we have a circle that is inscribed in a polygon. We say that the polygon is circumscribed around a circle, and the circle is inscribed in the polygon when each side of the polygon is tangent to the circle. When each side of the polygon is tangent to the circle. So this circle is inscribed. Inscribed is inside. That's how I always remember it. If it's inscribed, it's inside. So notice here, this circle is inscribed in the polygon because each side of that triangle is tangent to the circle. So we can say that either the triangle is circumscribed about the circle or the circle is inscribed in the polygon. And then the opposite of that, the polygon is inscribed in the circle. The polygon's inside the circle, so it's inscribed in the circle, and the circle's circumscribed about the polygon if each vertex of the polygon lies on the circle. When each vertex of the polygon lies on the circle. Angle. A central angle is an angle whose vertex is the center of the circle. It's an angle whose vertex is the center of the circle. And its sides are the radii of the circle. The sides of a central angle are the radii of a circle. So the central angle intersects the circle. It cuts the circle into two arcs. And an arc is just the 2 points on a circle and the continuous part of the circle between them. When we talk about an intercepted arc, it's in the interior of the angle. So if I had a circle and this central angle, this is your intercepted arc. And the rest of this is also an arc. But you've got your intercepted arc and then you've got the remainder of the arc. And we're going to talk about a little bit more about those. That intercepted arc is our minor arc in this case. This intercepted arc is a minor arc. It's an arc whose measure is between 0 and 180 degrees. An arc whose measure is between 0 degrees and 180 degrees. How many degrees are in a circle? 360 degrees are in a circle. And we could also say that a minor arc is an arc that lies in the interior of the central angle. in the interior. This is your minor arc right here. It's interior of the central angle. A major arc is an arc whose measure is between 180 and 360. An arc whose measure is between 180 degrees and 360 degrees. All right, and the circle that I drew up there, this is our major arc. The black arc is our major arc. Of course, I didn't get it right on the circle, but I think you get the idea. And then a semicircle is an arc whose endpoints are the endpoints of a diameter. An arc whose endpoints are the endpoints of the diameter. What do you think the measurement of a semicircle might be?
180.
The measure's exactly 180. Okay, it measures exactly 180 degrees. All right, here are a couple of postulates. I think these are on RenWeb, and the ones on RenWeb have some pictures that go with it that is sometimes helpful when you're looking at things, looking at your note cards. But the first postulate we want to talk about says that the measure of a central angle is equal to the measure of its intercepted arc. Okay, so intercepted arcs are measured by their corresponding central angles. So we'll look at an example in a minute at how we would do that. And then the second postulate, we've had the segment addition postulate, the angle addition postulate, and now we have the arc addition postulate that says if the intersection of two arcs is a single point, in this case we have arc DE and arc EF, if their intersection is just point E, then we can add the measures of arc DE to the measure of arc EF and get the measure of arc DEF. So the postulates, things that just are obviously make sense, they don't have to be proved. We accept them as fact. And it works just like the segment addition postulate and the angle addition postulate. So notice in the circle that I have drawn here, if we have a central angle of 70 degrees, the intercepted arc is 70 degrees. If I have a central angle of 40 degrees, the measure of the intercepted arc is 40 degrees. So if we look at arc DE, what kind of an arc is arc DE?
Minor.
It's a minor arc. How do you know it's a minor arc?
It's less than 180.
It's less than 180 degrees, and its measure is 140 degrees, because we can add the measure of arc DF and the measure of arc FE. What about arc DG? What kind of an arc is this? Semicircle. And what's its measure?
180.
180 degrees. Now, notice this next arc, I used 3 letters. We use 3 letters for a major arc. We use 3 letters for a major arc. I have sometimes seen 3 letters for a semicircle, but 3 letters for a major arc. And here, the measure of arc DGE tells me that I'm going from D to G to E. So what kind of an arc is that?
Major.
It is a major arc. And can we get the measure of arc DGE?
220.
How did you get 220, Cameron?
Because a semicircle is 180, and then you'll add it to the minor arc of,
Okay,
the intercepted arc of GE.
okay, so 220 degrees. All right, let's look at the next. Okay, we've already said each circle has 360 degrees. So what is the measure, Hannah, of arc PQ?
PQ.
130?
PQ.
Arc PQ,
PQ.
110 degrees. What is the measure of arc QR, Yuliana? 120 degrees. What about the measure of arc PQR, Monica? 130?
No, 230.
230. It's 110 degrees plus 120 degrees, which is 230 degrees. And the measure of arc PR. What would we do to get the measure of arc PR?
Add the 2 arcs and subtract.
All right, we know what PQR is. We can subtract that from 360 degrees. So the measure of arc PR is 130 degrees. Good. Okay, we are given that AC is the diameter of circle P. So, what is the measure of arc BC, Leah? 30 degrees. Pretty easy there. What is the measure of arc CAB, Shelby?
330,
And how did you get that?
180 plus 150.
180 plus 150? Okay, is there another way you could have figured that one?
360 minus 30.
You could have done 360 minus 30 as well. So two ways that you could look at that one. All right, what about the measure of arc ABC? Darby? 180 degrees. And the measure of arc AC, Kason?
180.
180. What's the difference between those two arcs? If they're both 180 degrees, what's the difference? Why use 3 letters in one and 2 letters in the other? Different parts of the circle? Okay. This tells us to start at A. If it's arc AC, it's telling us to start at A and go back down and around to C. If we have arc ABC, it's telling us to start at A and go up through B, then to C. So it's given us some direction. Which direction do we need to go? All right, and then the measure of arc BCA, Anthony? 180? 180, 210?
210.
Why is it 210? Okay. We'd have 180 plus 30, which is 210 degrees. And what kind of an arc is that? It's a major arc. All right, and then the last, this is another one you want to put in your note cards. But these 3 are on RunWeb. This one tells us that in the same circle or in congruent circles, that's important, in the same circle or congruent circles, 2 central angles are congruent if and only if their arcs are congruent. But congruent central angle means that we have congruent arcs in the same circle or congruent circles. In the same circle or congruent circles, congruent arcs mean we have congruent central angles. Now, could you have the same measure arcs, but they not be congruent?
Yes.
How could that happen, Kason?
If the radii are different.
If the radii are different. If you had maybe concentric circles, let's go back to the concentric circle.